Graphics in the media, the last piece of our lesson for today. So, one of the things that you try to do is you can possibly represent 2 or 3 more pieces of information by grouping it like this here, where you have 3 pieces of information for 87, 88, 89, and so on. And you can look at just the dark purple ones for its trends, the medium purples, the light blues. So you're able to compare over years within a single category, like the dark purples, or across categories like dark purple, light purple, and blue. Or make sure that you have a legend here with like pneumonia, cardiovascular, tuberculosis, etc. And the data is all displayed out. You need to interpret graphs like this that you see all the time. Even if you're not going to be a math teacher, if you're going to get into teaching social studies, science, anything where you're likely to categorize information like this and display it, things like color can really help make the information pop to kids. Imagine, if you would, that this was just a black and white graph and shades of gray, how much worse it would look. Okay, can do a 3-dimensional graph. This is of the data that was shown before. Does it give any more information than a 2-dimensional graph? No, looks a little better, that's all. Now, what about this one? Graphics in the media. As I take a look at this, this is trying to explain how much less a dollar's worth than it used to be. And what they do is they shrink the size of the dollar proportionally. So there are many 2-dimensional graphics that can distort our perspective, intentionally or unintentionally. So what you notice is that they're changing the size of the dollar to really emphasize its shrinking value. So, and sometimes they're accurate and sometimes they're not. You need to be aware of that. Okay, choosing a good scale is something that's very important to do. For instance, this is the same exact data. If you choose a scale that begins at 0, yeah, it definitely looks like there's fluctuation, but it doesn't look like there's overly dramatic fluctuation. If you choose a scale that starts at 30, you're like, whoa, look at the change that I'm seeing here. So reading a graph scale is a very important thing to do. And if you are the one teaching the class, how you present your scales will help get your point across to the class. Okay, here's another example: single family home sales. Look at the difference in the scale. We mentioned the break before. On example B, there's a big break in there. On example A, they jump right up to 300,000. Okay, same data, just a different way of presenting the data. Computer speed. If you notice here, there's a break on both of them, but what you see is you have to choose a scale when graphing data and reading a graph scale carefully. Realize that the choice of a scale can change the look of the data. So if you look at the first scale, it goes from 0 all the way up to 10 to the 11th, which is like an enormous, it's like 1 followed by 11 zeros. Not like it, it's exactly what it is. In the second scale, it's in terms of billions of calculations per second. So if you look at how much faster computers are getting in the graph on the left, it looks like they're increasing at a constant rate. They have a graph of a line. If you look at letter B, it's not so constant. It is skyrocketing because of the scale. In this case, the world population has been rising linearly, it seems, okay? But if you look at the scale of the graph, that could affect its perception. So make sure you look for the scale before you draw any conclusions. Generally speaking, by the way, population is exponential, not linear. All right, correlation and causality, the last thing we need to discuss here for the day. No correlation means there's no apparent relationship between the two variables, okay? Positive correlation means as one goes up, the other tends to go up. For example, generally speaking, the more money you have, the more your home would cost. Correlation, no correlation, might be the more money you have and your favorite kind of cookie, right? They have nothing to do with each other. A negative correlation says as one variable increases, the other decreases. So that might be something like the more you smoke, the less years you live. And then the strength of a correlation. The more closely two variables follow the general trend, the stronger the correlation. In a perfect correlation, all the data forms a straight line. Okay, so here's a picture of different correlations. First off, these are all positive. Correlations are like slopes. If the slope looks like a positive slope, as one goes up, the x and the y also goes up, that's a picture of positive correlation. One goes up, the other goes up. Now, if they're right on the same line all the way through, that's like a perfect correlation. It's one. Rarely happens, but could. Letter B, boy, that's really good correlation on letter B. That's more typical of a great correlation. That would be a strong positive linear correlation. And letter C would be a weaker positive linear correlation because as we draw what we call this line of best fit or a line of regression through this data, you can see that on the right one, graph C, yeah, as one's going up, the other's going up. It's not super densely packed like it is on B, which is a good strong correlation, and A, which is theoretical and rarely seen in this world, is at a perfect positive correlation. Not only do you have positive correlations, but you also have negative correlations. Negative correlation says as one increases, the other decreases. So in this case, as the x is increasing, the y is decreasing. That might be something like the amount of money, or better yet, the weight of a vehicle and its gas mileage. The heavier the car, the less gas mileage it gets, normally. So this is a perfect negative. They're all on the line. This is a very strong negative. Notice it's still a 0.9. The only difference is because it's a negative correlation, it's negative 0.9. And then we have a weak negative correlation for the same reasons we mentioned before. And it's possible to have absolutely no correlation. For example, how much money you have and your preferred cookie. Okay. Correlation and causality, a scatter diagram for diamond weights and prices. A positive correlation. So generally speaking, the higher the weight of the diamond, the more you pay for it. But it's not the only thing. There's also cut and clarity. Okay. So it's not the only factor, but generally speaking, yes, as the weight goes up, you tend to spend more. So there is a positive correlation there. Another positive correlation, income versus meals eaten outside the home. In other words, the more income you have, the more you tend to go out to dinner. And that makes sense because if you don't have money, you cannot go out to dinner. No correlation, moisture removal capacity versus weight. I don't know what it is that's removing the moisture, what's supposed to be removing it, but there's no correlation here. It's not, no clearly or even suggestion of a line that goes through that data. Life expectancy and infant deaths. This is a scatter diagram. This is a negative correlation because as your life expectancy goes on of a nation, okay, as a nation's life expectancy goes on, then you have less infant mortality. Possible explanations for a correlation. Could be a coincidence. Both variables might be directly influenced by a common underlying cause. That is definitely possible. One variable may be the cause of the other. Doesn't have to be, but could be. So guidelines for establishing causality. You look for situations where the effect is correlated with the suspected cause. You check that the effect is present or absent among the groups that differ only from the presence or absence of the suspected cause. Okay? For example, smoking. If you think that smoking is leading to a shortened life, you want to make sure you don't have obesity and diabetes and a bunch of other factors. Look for evidence that larger amounts of the suspected cause produce larger effects. Yeah, you definitely want to do that because that suggests a correlation. For example, if you smoke more cigarettes, that would produce an even younger death. account for other potential causes. That's what I mentioned before about diabetes, obesity, etc. Test the suspected cause with an experiment. And try to determine how the suspected cause produces the effect. Okay? All right, so that's a summation of guidelines for establishing causality.